This is Food Science 571, Food Process Engineering Technology. This is your instructor, Dr. Barrett T. Vaughn of the Food Nutritional Sciences Department. We are continuing with Topic 2, Physical Properties, Lecture 2 of 4. Continuing on with more physical characteristics, we have density. Density is defined as the amount of a material occupying a certain space. It's expressed as a mass per unit volume, for example, kilograms per meter square or pound per cubic foot. The importance of density is that you have a mathematical conversion of mass to volume. When it's needed, you need to use the density to do that. It affects the characteristics of container or package because of the density, and also it can influence product characteristics, for example, the texture, the mouthfeel, and this can be in foods such as whipped cream, ice cream, or butter. When you're measuring for a liquid, you can use a wide mouth pycnometer, a hydrometer, other types of equipment, and the specific gravity is actually the density of a material relative to that of water at a specified temperature. If the temperature is not specified, the density of water is 1,000 kilograms per cubic meter. And so the specific gravity is actually a ratio in terms of the material to water. And when you have particulate materials, there are three types of densities that you'll actually deal with: bulk density, particle density, and solid density. Density is expressed with the Greek character rho, which kind of looks like a P, but it's actually the Greek letter for R, rho. And what you'll see is that you have different kinds of densities that are expressed with rho some subscript. So you have solid density, which is rho subscript S, which is the mass per unit volume of a solid material and excludes any interior pores which are filled with air. The particle density, rho sub P, is the mass per unit volume of individual kernel, particle, or fragment, which includes pores within the particle. However, bulk density, rho sub B, is the mass per unit volume occupied by a large quantity of the kernels, particles, or fragments. Solid densities of most agricultural materials and food products are between 1,400 and 1,500 kilograms per meter. If the composition is known, the solid density is expressed by the equation that you see, where the individual solid density is the density for each component: fat, protein, carbohydrate, ash, or water, and M sub I is the mass fraction of that component. Here are some densities of common components of agriculture and food materials. And what you see is that between cellulose, citric acid, fat, glucose, protein, salt, starch, sucrose, and water, they all have different densities. Obviously, the density of water at a certain temperature in kilograms per cubic meter is 1,000. And you can see how some lie below and some lie above. And that becomes very important in understanding how it reacts or has relationship to water. Here we see the effect of temperature on the density of food product components. And what you'll find is that for different food product components, protein, carbohydrate, fat, ash, water, and also shown as ice, that there is a relationship of the density of that material actually to the temperature. And you see also the standard errors for those values. Here we have an example of density measurement, and it comes out of the book and it reads, "The density of an avocado fruit is to be determined. The avocado was first weighed on an electronic balance and then suspended in a beaker of water using a thin string tied to a ring stand. Care was taken to ensure that the avocado was completely submerged and that it did not touch the bottom or sides of the container. The weight of avocado was 219.8 grams. The container filled with water weighed 1,137.1, and when the avocado was suspended in the container, the beaker, water, and avocado weighed 13.553 grams. If the water temperature was 20 degrees Celsius, determine the density of avocado. In contrast, we also have the determination of bulk density. In this case, you pour the sample into a container of known dimensions, and you note that the method of filling and dimension of container affects the measurement. Also, moisture, method of drying, composition, particle size distribution, and particle shape affects the bulk density. Below you see the bulk density of several grains: barley, corn, oats, rye, soybean, sorghum grain, and wheat. Another important characteristic is porosity. Porosity is the percentage of total container volume occupied by air spaces when container is filled with particulate materials. This is very important when you're dealing with drying and aeration of a grain bed, and these are some of the equations from which you would actually calculate porosity, which you can imagine are related to both the bulk density as well as the particle density. Examples of total porosities are given below for oats, wheat, sorghum, soybean, and shelled corn. A physical characteristic that definitely will become important in certain kinds of situations is surface activity. Interface activities occur when foods are mixed. By definition, a foam is a gas in liquid. An example would be a whipped cream. An emulsion is a liquid in a liquid, which an example would be mayonnaise, which is a combination of egg and oil. A uniform distribution depends on the surface properties, and so detergents are used to reduce surface tension, which allows water to be adhered to different kinds of oils. You use a detergent so that they're able to actually mix. And then the surface tension is the force on surface of a liquid tending to minimize its area. Molecules within the bulk of a liquid subjected to equal forces of attraction in all directions. Those at the interface experience unbalanced attractive forces, resulting in a net inward pull. And you observe things like this when you have different kinds of liquids mixing with other liquids. Here you see the surface tension values of some liquids at 20 degrees Celsius. And you see it in front of you for water, ethyl alcohol, methyl alcohol, chloroform, and a number of different other things such as milk, skim milk, whole milk, cream, olive oil, and oleic acid. This becomes an important property in certain situations, and so it's good to know this property so that you'll be able to use it in the future. One very important aspect of foods is moisture in foods. It affects a lot of other thermophysical properties. It varies from 80% in fruits and vegetables to 4% in spray-dried milk or flakes. Solid, ice, liquid, water, vapor is humidity and air. These are all the different forms of water that can be actually in foods. Important applications deal with storage stability. You have water activity and equilibrium moisture content, which has to do with how much water and how reactive it would actually be in terms of storing it over time. You have drying and dehydration, where naturally with a dried food or dehydrated food, you want to be sure that you have a low amount of water in a product, which allows it to be stored longer and have different properties. Also with food transportation, the moisture in the food is very important. And then food marketing and profit, because when things are weighed by the pound, the more water that they have included, the more profit there would naturally be. Foods are biological materials, and therefore they have an affinity for water, and water activity actually is a measure of that affinity for water within a food. Here you see different water affinities required for growth of organisms. And so what you find is that There are certain organisms that can only exist with certain amounts of water activity. For example, you see at the top of the scale in terms of water activity, fresh and canned foods and vegetables, fresh meats, poultry, fish, and milk. At the bottom of the scale, you have dehydrated foods, crackers, cookies, powdered milk, things that have very, very low water activities. As you go up, you actually see in water activity, or increasing water activity, you see that there are different kinds of microorganisms that require certain levels of water activity. And the important thing to understand is that the more that you reduce the water activity through drying or dehydration or other means, therefore certain microorganisms automatically are not able to grow. They're not able to thrive in that environment, and that becomes very important. Pictured here is a chart of equilibrium moisture content curves for a peanut kernel. And what you'll find is that the relative humidity, which goes from 0 to 100 in percentage, and the temperature affects the equilibrium moisture content, which basically talks about what amount of moisture will be in the food and how that actually reacts with its environment. If there's actually more water in the air, which would be the humidity, depending also on the temperature, you can have more moisture content in the food that when you talk about equilibrium, you actually have the moisture not necessarily going into the food or out of the food, but where it's at a steady state. That is to say, there's no water coming in or out of that food. And so that's impacted by relative humidity as well as the temperature. And you see this here. A related topic when we talk about foods and moisture is the permeability of packaging films. Moisture moves from region of higher vapor pressure to lower vapor pressure. That is to say, foods dry out, crispy foods become soggy, and so the packaging material is used, one, to protect foods from a predetermined degree for the expected shelf life, and two, to advertise foods at a point of sale. However, the permeability is a measure of how well a certain gas or vapor can penetrate the packing material. And this permeability, shown as P, is a function of the amount of gas or vapor, the thickness of the film, area, time, and pressure difference across that film. Here you see conversion factors for various units of permeability coefficient. This chart here will become important when you are trying to convert different units in terms of permeability. This concludes the second lecture of Topic 2, Physical Properties. If you have any questions, please get in contact with me at the email address listed in the syllabus. Thank you.